Now I cannot hear. It's got muted.
Okay. Yes. I hear me. Okay. So this is a more physics view of all the transients, all the radio transients we have out there. So my mom is Hungarian, and there's a Hungarian saying, God has a big zoo, which is usually about people, but does also work for radio transients. So what we're looking at here is roughly, if you're going out in frequency, and then if we're going out in luminosity going upward here. So what you can see is the things that are closer to Earth are unsurprisingly, like, things like flare stars and brown dwarfs, not very luminous. But when you start going, further and further away, the things we see start becoming dominated by these more luminous events. So things like gamma ray bursts, things like that. The other big thing here to notice is there's two kinds of radio emission in radio astronomy, like everything kind of transient radio astronomy falls into two broad categories, coherent emission and incoherent emission. So when we're talking about these two things, we're basically talking about when all the phases are aligned, then that gives you coherent emission. So that's when you have something like a pulsar where you have these very bright beamed pulses, for example, or if you're going up, then you start having RFs and then the fast radio bursts, which you might have heard from, which come from beyond our galaxy and are this new enigmatic class. Those are all coherent emission. What I basically do though is incoherent emission, so things that are not like pulsars, not aligned like that. And so those are going to fall into more this blue side of the graph. So things like, supernova, solar bursts. And then we do start having, if you have relativistic effects, you start seeing things like GRBs occurring up here, and TDEs as well. And that's basically, if you have relativistic effects, it starts to beam and it starts to look like it's incoherent in our sphere. So that's kind of the radio zoo of transients that we see in the sky. And I really wish I had time to talk about all of these, but unfortunately I can't. So I'm just going to talk about the biggest space explosions that I've been studying because they're very exciting in my opinion. It's a relatively new field. And these are tidal disruption events. So what is a tidal disruption event? TDE occurs when a star goes too close to a supermassive black hole and it gets torn apart by tidal forces basically present between the event horizon of the black hole. Further out, you have a tidal disruption event is where that occurs. And so there's a lot of implications for studying these events. They're pretty rare. Supernovae, we think they happen about once every century in a galaxy of our size. These are about 1,000 times less common than a supernova event. But you do have huge implications if you can find a TDE for things like supermassive black hole environments. You can study those, including quiescent supermassive black holes. So AGN are a category that we can study very well, but those are active. So what's going on around these quiescent black holes, which are the majority of supermassive black holes in the universe? You can study things like relativistic jets. I'm going to get more into how we do that later. Outflows, that as well. And even maybe some multi-messenger physics. So for things like neutrinos, are there any associations for the neutrinos that we see in the sky there? To date, as I said, they're very rare. We only have maybe about 100 TDEs that have been detected, but most are discovered in the optical. And about less than 20 of those have been seen in radio. So if I can figure this out, I will play a movie because I promised a movie of roughly how we think these TDEs occur. So here is your supermassive black hole floating in its lonesome in space. And this is just a very visually pretty graphic. So we're going to watch it. And somewhere in here near this galaxy, we have this star. So perhaps through an interaction with something else, these galactic centers are fairly busy places. You usually have stars spinning around like we see around Sagittarius star. This star is, going to start going in too close. It's going to start extending, so spaghettification starts occurring as the tidal forces take into effect. And as you see, the star becomes unbound. This is much faster than this process happens, but the unbinding itself is just a few hours. And you see you have these giant outflows that get created. About half the material is falling into the black hole, and about half of it is going into outflows. You might get some jets launched, you might get other outflows. It's not necessarily just like a giant sphere around the thing. There's different structures involved in there. And this is going to play out for a very long, much longer period of time than the original TDE. Like, potentially years you can see emission from these TDEs after they originally happened. So, here's our black hole. Very exciting. Sorry? I think that's just artistic license here, because there's so you can get some obscuration once you have the disruption happen. But these are all point sources from our distance at Earth. So we can see that, okay, if there's, say, an accretion disk originally, then that could be obscuring stuff and stuff like that. So I think that's how this came into be for the simulation. Are there any other questions at this point? All right. So to give you a history really quickly of how this all plays out. So tidal disruption events were first predicted in 1988 by Martin Rees, who had a paper that I kind of like to read because he actually got most of the physics right today. So, he wrote this abstract. Stars and galactic nuclei can be captured or ideally tidally disrupted by a central black hole. Some debris would be ejected at high speed. The remainder would be swallowed by the black hole, causing a bright flare lasting at most a few years. So this is basically, you have super Eddington accretion that happens while this star is being disrupted. So you will get, as you see in this plot, very, very bright initial flash, and then it's going to be fading over time. Such phenomena are capable within the presence of 10 to the 6 times to 10 to the 8th solar mass black holes, the nuclei of near the nuclei of many galaxies. It turns out there's actually, the reason we have this, you need, I think he calls it like a stellar zone. Basically, if this black hole is too small, the odds of the star getting too close are not very high. So you're not really going to look for them around just stellar mass size black holes. If it's bigger than 10 to the 8th, the event horizon is going to be greater than the tidal disruption radius. So you're also not going to see these around the very biggest of black holes out there. And then I kind of like the last sentence. Stellar disruption may have interesting consequences of our own galactic center if a black hole lurks there. Ooh, so we'll tune back in on that. Anyway, but the whole entire story here of what you see here is they make TDEs. They're a very great probe for black hole accretion, understanding how black holes feed, what is driving that growth, how they're interacting with their surrounding environments. So here's a quick toy model of how TDE outflows work. And so this is just, as I said, a very quick picture. But what we're seeing here is, so you have a disk. So that's kind of what was in that illustration that gets created. You can have jets, but they're not all going to be creating jets. And there's going to be different parts of the electromagnetic spectrum are going to emit at different parts of it based off the physical process that's occurring. So if you're interested in the disk and what's going on, you're going to look in optical. If you're interested in the outflows, you're definitely going more into X-ray, so more higher energetic particles are occurring there. Radio, we don't think we're really seeing much from the disk, but we're definitely seeing a lot from these outflows as they occur and grow over time. So just to go into how radio astronomy works, is there any way to like lose this bar? Does anybody know, by the way? Sorry? Ah, okay. Hide which one? Floating meeting controls? Yeah, okay, cool. So just to go into a bit how radio astronomy works, because I know I left CASE even though I loved CASE because we don't have many radio astronomers here. So the first thing to note that we are studying synchrotron emission here. So we're just studying, the emission you get when electrons are spiraling in magnetic fields, whatever creates those magnetic fields, like an outflow or a shock wave, things like that. That's what we're really interested in, and that's the sort of emission we're picking up. The second thing to note is we're not discovering these TDEs on our own because basically radio astronomy is hard, and it's much easier to do a big optical survey. You have these telescopes now like Zwicky Transient Facility or Assassin, who basically look through the entire sky every night looking for supernovae. And then whenever they find one that looks like it's at the center of a galaxy, it's like a potential tidal disruption event, you'll take a spectrum of it, and then we have spectral information for what we think TDEs look like. So that's like, okay, that's a TDE. Now we're going to trigger in radio and look at it. Though, as I said, we're mainly interested in these outflows that have, occur for a long time after the initial disruption. So it's okay if, you're late by a few days or a few weeks or a few months, as you're going to see in this data set. So the third thing is we use a lot of radio telescopes to do this. And we also will then go and use survey data to go back and see what sort of information we have. Maybe there's already been observations of this system. things like that. The bread and butter of what I use is the Very Large Array in New Mexico, which is the telescope here pictured. So this is the interferometry is really what you're using, because then you can get very good resolution and very good sensitivity by adding together your telescopes. These are all, just to be clear, you don't go out these days to take the observations. It's like anything, it's remote. But I did go out once for a site visit. These are all the size of buildings. Like, it's very hard to say how exactly huge these dishes are. You literally have railroad tracks and you'll move them around for different configurations and stuff like that to sort of see different things. So what basically happens is you have a program on the VLA and you're like, I'm gonna look for TDEs, and you get triggers is really what it is. So once a new one is discovered, you tell the observing people like, hey, I'm gonna use one of my triggers to go look at this object, and then they're gonna go look at it for you, and then they'll tell you the data's in the archive, you go download it in your office, and that's really kind of how we're doing this sort of research. And what, as I said, these outflows generate synchrotron emission. And what we're really interested in here is we're going to be taking multi-frequency observations. So over a span of frequency, usually from like say 1 gigahertz to 20 gigahertz is what we're talking about. You're gonna take several observations and you're gonna get a different flux at each one. So I'm gonna show you guys at some point in here, there's a radio image. It's basically just a point source in an image and you're measuring its flux. It's nothing, you know, getting the image is hard, but the information in itself in it is somewhat straightforward. But there, you get a lot of physics out of that, and that's because we have gamma ray burst physics was a huge, huge deal for many years. We have a lot of theorists who worked on the problem of gamma ray bursts, and we're applying that to TDE physics because they're very similar, very high energy environments. So what you're seeing here is you have different breaks basically that you're going to have in your spectrum caused by different things. So like you're going to have mainly the peak frequency and the peak flux, and you're going to extract information from that. And then what you can also get out of this is different types of physics. So for example, excuse me, based off the model we have here, you can extract information such as the radius of what is emitting, the energy of it, its magnetic field, even the density of the material it's smashing into. All these things we can actually derive just based off the spectral SED here. We also can learn a bit about shock physics. So, you know, we have all these electrons, they're not all going to emit in radio. So that's called, you know, the shock emissivity and the magnetic emissivity, this epsilon E, epsilon B term. Usually, for example, people will say, oh, it's just 10% because we're astronomers and everything's just 10%. But you can actually, when you're looking at these higher frequencies, it's determined by this break here. And if you see a break in that cooling frequency is what it's called, where that break occurs, that can tell you a lot of information about the shock physics as well for what's going on. So to give you guys some ideas of how this all goes forward, I'm going to go to the beginning of TDE physics, or when it really began for radio at least. It was an object called Swift J1644 plus 57. So called because Swift was the X-ray satellite that detected it. And then those are the coordinates of the object. And that's basically everything in astronomy, how we name things. So as you see, it was detected March 28, 2011. So it's about 10 years ago in a galaxy of Z.354. So over 1 billion light years, I think, something like that. But the interesting thing here, so Swift is in the business of looking for gamma ray bursts is really what it is. And those you need to see within minutes. So they swim really fast to these various targets. And at first they thought this was just a gamma ray burst. And then the weirdest thing happened, this gamma ray burst didn't turn off. Like it just kept going. And people were very confused by this, and all the astronomers scrambled to point every telescope in the sky that we had available to it. And what we ended up seeing was the first radio detection of a TDE, and people realized what happened was this TDE occurred, and it launched an on-axis relativistic jet directly toward Earth, and that was what we picked up, and that's why it was so honking bright. That's where all this radiation was coming from. And it's the best studied case of an on-axis tidal disruption event to date. I should note, so this happened in 2011. Everyone was very excited. A second one was seen in 2011, just further away. So everybody was even more excited. A third one was found in archival data from 2011. Everyone was really excited, and we have never detected another one since. So it's, you know, when you're kind of just using the universe as your laboratory, you're really, subject to what the universe gives you is kind of the problem here. So if you're wondering for some of these things, is this typical, is this not? The answer is we really need another jetted TDE because that would answer a lot of our questions. But yeah, so what happened though is this relativistic jet happened. It was very exciting. And then around day 500, we usually measure things in terms of the number of days after the disruption happened. The jet turned off. So I'm going to show you guys how you can see this. So what we're seeing here is actually the SWIFT data, so the satellite. You can see there's a lot of variation occurring in this X-ray density as it's going on. We think that is because there was material that kept falling onto the star and feeding the jet was really what was going on. And then after it turned off, this is what we said was the turnoff. So, or well, the people who wrote this paper rather. But so you can see that's the last SWIFT point. And then this data point is from Chandra, which is a more sensitive radio telescope launched about 25 years ago now. And what you can do though is, because as I said, we had this radio emission, you can extract or extrapolate the radio emission, you know, it's on this curve. If you keep going straight down all the way to X-ray, so a very long way down the electromagnetic spectrum, that is what you expect if you just had synchrotron emission from a shock wave that is going outward. And it matched perfectly what happened, what you expect from if you no longer have a contribution from a relativistic jet. So this was incredibly exciting, and it's very hard to explain how big a deal this is if you're into jet physics and understanding that process. Because I mean, a year and a half, like that's a postdoc, right? Like you can do that in a lifetime. Normally jets, you know, they're hundreds of thousands, if not maybe millions of years in existence. So this is just a really good way to study these and to understand this one data set. As I said, though, unfortunately, the other two are too far away to get these detailed measurements. So this is, you know, the biggest and best of these jetted TDEs that we have. And so, you know, I got involved in this group that was doing this research just at a much later time. So, and the thing is, this thing is still bright in radio. That shockwave keeps going outward, you know, the only thing stopping it is the more density that it keeps running into over time. And we can basically still check it out with the VLA and see what's going on. So the latest update finally got published this year. And so these are two of these SED curves that I was telling you. As I said, you can see we're going from like about 1 gigahertz to about 20 gigahertz. You're doing MCMC, so Markov chain Monte Carlo simulations with your models that you're expecting to see what's going on here. And then this is the second one. So this is fading over time, right? Just a very slow period of time. So triangle means upper limit. We did not actually get that peak flux. So then that's why the Monte Carlo MCMC is not getting you as tight parameters as it is for the other one where you got the entire curve sampled very nicely. But yeah, so this emission is still, you know, consistent with a forward shock as it's going outward and stuff like that. So interacting with its environment. And then the other cool thing is, you know, you can kind of take the light curve. And as I said, you go through and there's all sky surveys and stuff you can look at. And we detected this object as well in VLAS. So the VLAS is the Very Large Array Sky Survey. Usually when you want VLA time, you have to apply and, you know, go through ATAC and all those details. But what happened here is the VLA is also doing a new sky survey. They haven't done one in about 20 years. And they're basically doing it 3 times around the sky, about 18 months in between. And it's like, you know, just kind of snapshot images. So usually most things are not bright enough to see there. But there's been a lot of talk lately about can we detect TDEs or other transients maybe lurking in that data set. You know, if you have 3 observations over 18 months and a student who really likes to do, you know, machine learning type things, are there any in there? And so because we did detect it, we can actually have very good predictions for how many of these might be lurking in the VLA Sky Survey. And we said that probably about 100 of these TDEs, relativistic ones, either on axis or off axis, exist in that Sky Survey. So, you know, a bunch of grad students can go be sent and look to find them. So that's pretty cool. And also, as I said, you can look at the luminosity. It's fading what you'd expect if it's just a source expanding slowly in an optically thin regime. The other thing we can do is we can talk about the steepness of the curve that I was showing you guys earlier for that SED. So that's basically set by the energy index P, which is dependent on particle acceleration. The interesting thing is that we think there might have been a change in this curve as the evolution of Swift J1644 plus 57 happened over several years. So basically it was first 2.5 and then we measured 3 after 100 days. The thing that's kind of curious though about that is, you know, I did this detailed analysis because the data is like really nice here, but also these first observations were just not very constraining. So is this a real thing that happens as TDEs get older and evolve, or is this just a thing that comes out of the data? It's not completely clear, but you know, we need more TDEs, I guess is the answer here. But the other thing you can do, as I said, you can do modeling, get some updated parameters. What we see at these late times is the flux, the peak frequency, they all just start decreasing over time. There's no energy, for example, being injected to the system anymore. It's just fading. And then we can study the evolution of this outflow. So what happens when you have the evolution of the outflow? As I said earlier, you can basically assume a non-relativistic system. This is no longer relativistic, so it makes life a lot easier. And you do what's called equipartition analysis, and you get the radius, the energy, magnetic field, and number of electrons radiating from an emitting region. You do kind of have to make assumptions to get the density for the shape of that emitting region. So, you know, if it's a jet and the majority of your energy is coming out of that jet, then it's of course going to be a much higher density that you get than if you assume like a larger volume, such as like a sphere or something like that. But yeah, this is all consistent with Newtonian expansion, as you can see. This is the model we had, and as it's going outward, the energy is just slowly decreasing. So what you kind of expect from a tired system going further out. But the interesting thing though, yeah, for the system is also it's going to be visible for a very, very long time. Radio emission, it just is around for many, many years. So to give you guys an idea, so these are 3 different frequencies, and you can kind of say, okay, this is how my luminosity is changing over time. These 2 data points here are just our last 2 observations. So especially if you're going out here, so VLBA is a very long baseline array. So that's if you're doing telescopes linked from like Hawaii to Puerto Rico or something crazy like that, you know, type stuff. This is the VLA. This is the next generation VLA, predicted sensitivity limits. So we're still very much waiting for the decadal survey in astronomy that'll tell us, you know, what are the next big projects. The NG-VLA may well be one of the top ground projects because we really kind of need an upgraded VLA. But, you know, you're basically going to be able to study this object, especially at lower frequencies for, you know, longer than my lifetime. It's going to be visible in the sky. Just as I said, fading very slowly. And, you know, as I said, there's a lot of these out there. It's going to be interesting to see how this evolves. But the sad thing is, but not in X-rays, these are of course much more energetic photons. So we had observations as well from Chandra X-ray telescope, and the NRAO have a very nice program where if you apply to use Chandra or the VLA, you can also get Chandra time at the same time and vice versa. So our group applied twice and both got approved, so you get 2 observations, right? But it's pretty clear that this X-ray emission has just kind of faded out over time and it's no longer detectable. What you can see here is, though, that's kind of interesting, is the system, as I said, you have this electron emissivity question, and how much of that energy is going into the magnetic field from the electrons. And what we can see, though, is if we're extrapolating from radios, I was showing you guys earlier, when it was still the jetted TDE turning off, we still don't have, you had both of these parameters the same. It's called equipartition. We actually have a deviation from equipartition here, which looks to be like, instead of 10% of your electrons going into your magnetic field, you're only having 1%. So this is actually like not as big as you'd expect just from theorists writing stuff down, which, I mean, because I know there's a lot of physicists here and you guys can go to the lab and literally twiddle your knobs and stuff like that. It's kind of hard in astronomy to know how to basically constrain your knobs and what to, you know, figure out. So that's why these sorts of numbers are very important. So as time has moved on, because, you know, SWIFT J1644 has moved on. So this is the radio luminosity. We've gotten many more TDEs. And what we're seeing is we're starting to get a few different things in the zoo of TDEs. So we was talking earlier about the zoo of transients. This is now the zoo of TDEs. What we're looking at here is we have the time since disruption and then just the radio luminosity, so how bright it is. And you can see there's a huge variety here in what is going on with these different things. So in this plot, if they're just like the gray triangles are upper limits, so you're not detecting those objects. As I said earlier, only a fraction of all the TDEs we know actually emit in radio. what we're seeing is, maybe 20, 30% or something to be, that 30% is probably too generous actually, if anything. But you also have a lot of variety in terms of what is going on here. What we think is happening is, so as I said, there's on-axis jets, so jets pointing directly at you, off-axis jets, ones that are not pointing directly at you, and then you have non-relativistic outflows are the last ones. So those are more akin to like when a supernova has a shock wave that goes outward or something like that. That's the similar energy and things like that that we're thinking about here. And right now, what we're seeing, so as I said, this was 2011, and we saw 3 jetted ones directly pointed at us. We haven't seen any since. We're estimating about 1% of all TDEs are in that jetted category. And the reason is just, well, it might be even lower. It's just statistically we're sitting around waiting, and that's kind of the number we've reached. So as a quick side note, because I get this question sometimes, can you have a partial TDE? So can you have something where, a star goes, but it doesn't quite get completely disrupted, like just a little bit of material keeps falling onto the black hole or something like that? And there's been some work recently in this that we kind of worked in a little ourselves, so I just wanted to touch on this. There's an interesting transient called Assassin 14KO, detected, as I said, by one of these supernova all-sky surveys. And it is flaring every 114 days with a period derivative that is very precise. These guys can predict when they're going to see their next flare. And they've interpreted this as a partial TDE. So the star does not get close enough to the supermassive black hole for complete disruption. And then, so what is going on? We actually triggered, this is a Southern Hemisphere object, MeerKAT, which I'm going to talk more about in a bit, in the Southern Hemisphere. And it's a very steady source at radio frequencies. So it's basically akin to just if you had an active galactic nucleus out there. So just, if you have gas and dust falling onto it. The other thing to note about this object, though, is like, this paper came out, everyone was very excited, and then, more people start to look at it. The first thing to note is there is a second AGN in this very galaxy. They say it's not close enough to matter, but okay. And there's also signatures that there was a previous AGN merger. So someday when LISA, goes up, we're going to detect supermassive black hole mergers. That sort of thing is what, they think we have evidence that that's what's going on here. So usually in astronomy, when you start to have like a few weird things going on, then it's like, well, it's most likely an AGN is always what we say. So I'm not completely convinced that partial TDEs, like if they might still exist, but this is probably evidence of some strange AGN behavior, not actually that. But I can tell you a bit more about, what an ordinary TDE looks like. So as I said, most of these are just these non-relativistic ones. And this is going to be a little bit about AT 2019 DSG, which was first detected in 2019. And I submitted a paper. It's actually going to come out next week, and we might have a press release on it. So that's kind of exciting. And it's been a very exciting TDE because it's been probably the best studied one other than Swift J1644 plus 57 to date. There's just a real wealth of data at all frequencies and things like that. And what's kind of been interesting as well about this is there was a recent paper by a group, Stein et al. 2021. They argued for a neutrino association that was coincident with this TDE. The trick is, though, they argued that this neutrino happened on October 1, 2019, which is about 5 months after the initial disruption event. Though, that doesn't stop theorists from going and writing a ton of papers on how this is clearly how this neutrino happened and stuff like that. So, it's completely an association argument, but, there's certain energies that they argued and stuff in this paper with a very small sample of radio observations. So how can you be sure? Well, you can, of course, take radio observations that are just a lot better using the VLA, so 1.5 to 36 gigahertz. And we also used ALMA, which is the Atacama something, it's down in Chile, and it's a more at 100 gigahertz, so higher frequencies, in order to understand what exactly is happening in this TDE system. Oh, and I should also, the reason also this is such a well-studied one is it happened much, much closer than a lot of other TDEs. This was only 230 megaparsecs away. So that's, for these sorts of objects, quite close, trust me. So, we took a lot of data with the VLA. What we're seeing here, so as I said, there were 4 observations that were, the yellow ones were from the previous group. So because it's published data, we kind of snagged them and threw them through our algorithms as well, because why not? And we also took a ton more data of our own just to see what exactly was going on. It's on the archive. You can go look to your heart's content at all these beautiful SEDs. Trust me, they're beautiful, you know, if you're the one who made them. And we can update parameters. And so we start seeing some interesting things that are going on here. The first is, so the peak frequency, so, you know, where the highest frequency, that's just steadily going downward in a pretty linear trend if you're looking at this plot. But the peak flux actually is increasing for the first few months of time. So that's kind of unusual, like maybe there's some sort of energy that's flowing inward. Maybe there's something to do with the expansion of this shock wave as it's going outward. There's a lot of interesting things you could maybe potentially be contributing to that. We can also, though, do an equipartition analysis to see what's going on here. And, but yeah, also I should mention, this is the first ever detection by ALMA of a TDE. So this is the, here it is, Atacama Large Millimeter Submillimeter Array in Chile. If you've seen beautiful images of protoplanetary disks forming, that's ALMA. That's like really usually what they do. But also you get radio emission just nowhere near as bright. It's just a very sensitive telescope at these higher frequencies. And what we can do is, because we had a detection and then we had a constraining upper limit here of this TDE, we could do that equipartition analysis that I was talking about earlier. And then we could see here that there's a cooling break. It's about roughly 25 gigahertz is where this cooling break occurs. And that corresponds with electron emissivity 0.02. So this says maybe 2% of those electrons are going into this. And it's not as extreme as for Swift J1644/57, but it's definitely there. You don't have just an equipartition system going on. This is important because later when you're calculating your things like your energy, then that is going to severely depend on how much energy you're assuming is in your system. So if you're arguing, for example, that there is a neutrino and you want to have a high energy, maybe you're going to say that, you know, there's a huge deviation from this. And so each electron you see has a lot more energy in it than just, you know, there's more electrons than it's lower energy. So as I said, we have the evolution of the outflow using these parameters, and it's very consistent with the Newtonian expansion. So the other idea is, okay, you see this new TDE, maybe there's a jet there. Like, how do you know? You have to do a lot of, you know, clever analysis to figure that out. It really doesn't look like that to us as this is going outward. As you can see, it's really just kind of similar to what I showed at lake times for Swift J1644/57. It's expanding. The magnetic field is slowly going down, things like that. And then I kept talking about the density, and I kind of just saved that because I wanted to show this plot, because you can also learn a lot about these by comparing the densities of these different TDEs and what we're seeing in the density. So what we're seeing here, so this is density, and this is radius when you're basically dividing by the Schwarzschild radius of each black hole. So the idea here is each black hole is not the same size, right? So it's very, you can't just say, I'm literally only looking to this distance. It doesn't really work that way. So you're kind of trying to get a universal unit here. And then we can also plot the density compared to different galaxies that we have this information for closer to us, such as within our own Milky Way, and for M87, so the picture of the black hole black hole. And what you can see here, it's kind of interesting that Swift J1644/57, similar, it's very low density, similar to M87. There's a lot of the density as it decreases is, you know, R minus 2.5. So that's basically telling you about how the material is falling into the black hole over time and things like that. The thing that's really interesting to me, though, about a lot of this data is we actually know the density profile surrounding these supermassive black holes much better for these TDE black holes than we know for our own Milky Way galaxy. Because, you know, there's a lot of dust and crud in between us and the center of the Milky Way. This is very hard observation to make for our galaxy. But when you have a very bright radio source, even if it's very far away, you can measure this to, you know, very good levels. So if you really want to know what the environment is around these quiescent black holes or things like that, you really need to go and study TDEs. That's really where this information is. So that's been pretty cool, or like, as you can see, not very many TDEs, but we're filling out this plot, and that's very exciting. The other thing you can look at is the energy and velocity of all these TDEs and sort of how it comes together. So what we're seeing here is on the bottom, we just have velocity. So relativistic versus non-relativistic. In between is this weird thing called mildly relativistic, which, you know, the theory starts to become a bit more complicated about. And then we just have the energy. And we're really starting to see that there's two populations of these TDEs that are emerging in energy here in particular, and the velocities. So the first is the sort of jetted TDEs. And so they're living up here. And this is similar. So if you have a gamma ray burst, so you know these huge, very energetic supernova explosions that launch a gamma ray burst, gamma rays, then that is up, they're up there. They're very energetic, they're very relativistic. By the way, I should note the interest, you know, this is, it started here and this is where it currently is, right? It's not going to the right, it's going to the left there, it's decreasing. But then also we have the second population. They're very clearly isolated and secluded from the first, which are basically, they're more similar to what you see from supernovae when you're looking at supernova energy and velocity and things like that. So we're really starting to figure out what exactly is going on in this TDE population. But yeah, so to go back specifically to AT 2019, DSG, I did promise you a little bit about neutrino. So what about this neutrino? What did we learn? And so, as I said, this was a neutrino association. They said it was about 5 months after the detection. They reported in their paper, if you go, these higher energy levels that require a very low electron emissivity based off of Swift J1644 plus 57 data to say, look, we have very high energies and we have this neutrino, they must be related. That's kind of where their argument came from. And then when we did our analysis, and because we had this Almond observation and stuff like that, we're like, no, it's actually much closer down here to this value. So that's not great because it's kind of hard to say, my understanding, why a neutrino launched based off of those energy levels. So there is another question though, like, what could you do? You know, you can make the energy even higher if you had a jet. I think they also did that in the paper. But if you look at our data, if it's even mildly relativistic, you can just say, I have this radius, you know, what do I have to do to have a jet to have that happen? You basically have to have a jet that's 2 degrees in size. That's already based off what we know from gamma ray burst physics, a pretty darn narrow jet. Once you get to truly relativistic jets though, it's just physically unfeasible. So, and also finally, there's kind of just an argument you can make. Well, as I said, this is similar to type 1A, 1BC supernova, typical supernova explosion. Where are all the neutrinos we're seeing from those? Because we see a lot more of those a lot closer than we see from TDEs. So I think at the end of the day, my personal opinion on this is, you know, if you hear hooves in the night, think horses, not zebra, because it's really kind of hard to justify. Like, I know neutrino associations are very difficult, but I think we definitely need a bit more evidence before making that conclusion here. So just to wrap up, I wanted to talk a little bit about the future of these TDE programs because, you know, talked about these individual objects and, you know, look at this beauty and this and that feature, but we really kind of need more to understand what's going on in these TDE populations. So it's kind of like you currently have the individual snowflakes and you can look at the snowflake and admire it for its own unique abilities, but you really kind of eventually need the snowbank, right, to figure out what exactly is going on in this TDE population. What sort of properties are we seeing in the physics about them? So we kind of have 2 things that we're doing lately. The first is we have a VLA large program. So if you're applying for a ton of time over several years, you can apply to the VLA and be granted, you know, a ton of triggers instead of each individual TDE. So I'm a member of this. We began in November 2020. And we're doing the first sort of comprehensive study of these radio TDEs. I think we've triggered 7 times and there were 4 or 5 detections, so that's nice. And then I'm also involved. I got time on MeerKAT. So that's the this beautiful telescope here. It's in South Africa. So the southern sky basically has been a bit neglected compared to the northern sky in many areas of radio astronomy, not just this, just because you didn't have this telescope of equivalent sensitivity to the VLA in the southern hemisphere. That is thankfully now changed with MeerKAT. It's a very cool telescope. By the way, it's a MeerKAT because it was the Karoo Array telescope. They had 22 antennas and then they got money for 60. So Meer is more, so more cat, I guess. Anyway, I thought that was fun. And also you actually get these beautiful images. They're the prettiest radio astronomy images I've ever gotten. So they're very wide field. That's kind of what they're doing. So I actually cropped this. I had a TDE and it was detected, but it's like all the way over there. But you know, you're not going to post that picture. But these are just beautiful AGN I keep getting distracted by in these data sets while I'm doing my astronomy. So I thought, they do look worth sharing. And yeah, so these are just, non-star destroying black holes far, far away. But the nice thing is, so we started looking at these older TDEs, so things that we were not able to trigger on when they first occurred in the Southern Hemisphere, because MeerKAT had its first call just last year for people who are non-South Africans to use it. And, we have detections. We have our first detections from this. So the data analysis is ongoing. And also, I should mention, these late time observations are important for TDEs. So we actually started having a few papers coming out on this. So there was a recent paper that showed you're having radio flares from a TDE that was radio quiet for the first several hundred days. And then you start having flares, hundreds or even, 1400 days post disruption. So normally, because you have to justify your telescope time, if you don't see anything the first, 60 days or something, you're probably not going to keep looking at it. But the flares we're seeing, they're from, similar to what we see in AGN, and it does not correlate with the X-ray. So we have now questions. So like this outflow, as I said, this is a process that takes a long time. Can you maybe have, more radio emission that we're just completely missing right now because we're only looking at the initial flash and bang? The answer is yes. So this is literally like, I started this 2 weeks ago, but it was like really cool. So I wanted to tell you guys about it. So there was a TDE called PS16DTM, which was very well studied because it was a previous AGN. So you could go into the Sloan Digital Sky Survey and even get a spectrum and stuff like that to see what's going on in this thing. And it was published in optical mainly data. They looked at the time to have very constraining radio limits. Within the first 5 months, there was no radio emission from this thing. We looked again though in 2021, and this is a detection. So as I said, these images are usually not as pretty as the MeerKAT one. This is a very large array image. And you wouldn't really know unless you had previous information that this new dot in your radio sky is actually a TDE, except, we have the optical information to tell us this. And so I did some preliminary analysis on this. It looks like the outflow is about 2,700 kilometers per second. So that would be pretty slow for and this is literally just 2021. We saw it in 2016 in velocity. This is a very crude calculation. But the idea here is just that, yeah, this is a very slow outflow. Maybe it's a very low density environment further in. So you literally didn't have enough stuff to run into to produce the radio emission that we see. It's also just very slow. Does that maybe affect it? Maybe there's just, different, the energy never quite got injected, things like that. So there's a lot of questions here. The crazy thing though, is this is just one TDE of about 35 late time TDEs in our current sample. I'm not saying they're all going to be like this exciting and this interesting. There's still a lot of, upper limit detections. So some of these are really never doing anything. But it's a very exciting new area of research that we're just starting on right now to figure out what is exactly happening in this broader population of TDEs. So to conclude, I hope I convinced you guys that, TDEs are pretty rare, but they're very exciting. It's kind of a new subfield in astronomy to figure out what's going on around supermassive black holes, both as they tear things apart, launch relativistic jets, have outflows that go out and interact with other things. Radio astronomy is a very important part of this. So we can learn about the outflow, for up to years afterward, extract various parameters such as the density, how big it is, things like that. And yeah, there's still a ton of work to be done, especially in these late time TDEs. This is such a new field. We literally, don't have enough objects that are old enough to look at this. So this is kind of interesting to see as this is evolving over time. Finally, this image. So as Cyrus says, I'm a science writer sometimes, not as much now that I'm a postdoc, but I have a feature in the December issue of Astronomy coming out, and they did this beautiful art for me, which I rather like. So I decided to use it. So if you kind of want more a layman's perspective, I'm going to plug that for a second. Yeah, and that's it. Thank you very much.
This is like maybe like a really basic question that knows, but could you say just like a little bit about what is a jet and why does that happen?
So, sorry, I should have probably gone into this earlier. Yeah. So a jet is just when you have a beam of material. So like this here is a beautiful jet, right? So this is, you have a black hole in the center. This is probably just gas falling into it. and it's launching this material basically at relativistic speeds, and that causes the relativistic jet. We don't fully understand exactly how this happens. This is actually one of the big questions in astrophysics to figure this out. The thing I'll note though, because it's relativistic, that's why you only see one jet and not two. It is launching in both axes, but because that axis is away from us, it's Doppler shifted away from our wavelength. So that's why you don't see that one. Does that answer your question?
So the thing they're looking at, you get some swirling in, and then for some reason it's perfect.
Yeah, so you have something probably along some sort of magnetic field axis is what we think for supernovae, at least for gamma ray bursts. Yeah, so you have these relativistic jets that get launched, and the details about why that happened, to be clear, like we don't understand why this TDE did that. Maybe it had some sort of previous encounter or something like that, but it's very hard to say for sure when you only have one very well detailed model. So
We should be hearing a question from Ben.
Oh, sorry, I was typing. Have we seen any TDEs occur in galactic nuclei that were already active? And is there any evidence of like seeing the arriving star disrupt or torque or something the torus or the jet before it was torn apart?
yeah, sure thing. So yeah, so to repeat the question, the second question, because I was going to answer that first, was can you see these stars before they go in to be disrupted? The answer is no. These are so far away that unfortunately you really can't resolve the individual stars. For Swift J1644 plus 57, they did the math and it was significantly less than the mass of the sun that created that disruption and things like that. I haven't seen that information for more recent TDEs. I think that might have been something specific to the physics about that event. And your other question was if they were AGN active or active before we saw them, or these are only quiescent supermassive black holes.
Yeah.
Answer is it's complicated. And the reason it's complicated is because in radio, AGN do a lot of weird things. Like they flare a lot. They can sometimes flare to luminosities that are very comparable. So it does become a bit of a question then. So like, is this just a very active AGN flare or is this a TDE event? And you definitely have some where, the guy will write the paper and be like, this is totally a TDE. And everybody's like, okay, Bob. And, though I will say, so the one that I was showing you guys, this guy, this was a previously known AGN. And so that's kind of why this is exciting, that it was not a radio bright AGN. We have very good data on this thanks to the Sloan Digital Sky Survey. And now we have radio emission. So how often this happens and things like that, that's still a really unexplored parameter space. Mm-hmm.
So, and we're also doing some weekend monitoring and transits. So my question then is, how do you say it's the TDE versus just the interchangeable AGN or just radio?
Yeah, sure. A lot of that really. Oh yeah, sure. So the question was, how can we tell the difference between what is a TDE and what is an AGN? The answer is usually in the optical spectrum is really where you're getting that information from. So I don't remember the exact things that you're extracting from the spectrum, but they are sufficiently different from a typical AGN spectrum that it's like, okay, this is clearly a TDE versus not. I'd have to look it up exactly. I could tell you after if you're interested. Yeah.
So this is based on SPSS spectrum.
Yeah, so this is currently based on SDSS spectrum. Yes. Okay, so the question was, can we tell why the electron emissivity and the magnetic field emissivity is different? And the answer is, I don't think so. I think this is just, these are two parameters that, theory says that we need to have. And in gamma ray burst physics, they're usually the same. And then, but it turns out in TDEs, it looks like they're different. Yeah. Sorry, does that answer your question or? Yeah, I'm sorry. I wish I knew too. Right? So,
I put it in the chat, but I don't know if they all know. So this is for the Zoom audience. You're welcome to ask questions too. Just raise your hand using reactions or put it in the chat and we'll call on you. Okay, let's go on to the next one from here.
The black hole would be like snacking on a large amount of gas, or would that be unlikely given the amount of emission?
yeah, sure. So we see that that's what an active galactic nucleus is. We think that's just gas falling onto it. And we actually have pretty good data thanks to our own supermassive black hole, because we've seen, you know, radio flares for much longer and much detailed precision there. So yeah, what basically happens though is, so when you see a TDE, like something like especially Swift JC, that is just like, you know, going to be 10 times brighter than the brightest AGN. So something like that, then it's like, okay, this is clearly something related to that. Also, as they fade over time, AGN don't necessarily need to fade, say, linearly. So I was showing you that was a very like slow fade. AGN don't really do that if they're active. Like they're always kind of changing very much in their luminosity and their brightness. So that's kind of a giveaway. So there have been people, as I said, going through the sky surveys and trying to find old TDEs that, you know, maybe happened in the 1980s. So well before you would have ever detected these things. And they have found a few of these where it's like, okay, something fading over time. I mean, that's never going to tell you, because if you never saw the original, you'll never know for sure. But it does seem like those are more what we expect from TDEs over AGN. Oh, within our own galaxy? I don't think so, but I could just tell you it'll be really honking bright. You know, I mean, there's a lot of dust between us and the center, so not an optical necessarily, but everything else, I mean, if something like that were to happen in our own galaxy, we basically would only be studying that for years, because it would just be so bright it would drown out all our other astronomical sources in radio, at least. But that's the same with the galactic supernova, right? And this is even brighter than that. So that's why I'm just like, okay, yeah, we'd all become TDE experts.
It seems like there's a lot of interesting, exciting particle physics. Are they conjecturing neutrinos because of missing energy, or because they know that there's some process?
Yeah, so I think the idea is, you know, we have a lot of neutrinos and we don't. So sorry, Bob's question was, is the neutrino and the association there to do with the energy? Is that right?
Yeah, so I just thought, why did they think they needed them?
Oh, so I don't think, why did they think they need it? I think they found this neutrino and then we're like, oh, let's see if we can have a coincidental source that might have created it. And then there's TDE happened. So as I said, it was 5 months after, and it's like, you know, I'm not a neutrino physicist, but I was a particle astrophysicist myself at one point. And I remember the first Auger paper where it's like the associations and then the association disappeared. So it's very hard, but yeah, one event is harder. If I hope I didn't offend anyone with that. Sorry, I heard, what's the difference between a TDE and a what? A pulsar or a quasar or a blazar. Yeah, sure. The big difference there is, so what's the difference between a TDE and a quasar or a blazar? Those are basically very steady state sources. And those don't really vary very much over time, whereas this is like you have that initial super Eddington luminosity that happens and then it's fading over time. And so that's really kind of the huge difference here. The luminosities can be comparable even to quasars, even though those are like very early universe, incredibly energetic sources. But if you have a jetted TDE, that's pretty up there. Corbin.
So you showed these two populations in a plot that had velocity.
Mm-hmm.
And one of the populations with this huge amount of airport had a part of the sample of the velocity evolving to the left. So physically, what's the idea of why would that velocity evolution happen? If theorists were to explain, say in a movie or something, why velocity would change that?
Okay, so Corbin's question was why the velocity is changing over time going toward the left in the plot that I was showing of the two populations, energy velocity. The answer is just the material surrounding this TDE. So you have this, outflow shock wave going outward, and it's literally just the material as it's hitting it going outward over time. It's very similar once it's no longer relativistic, we think, to like supernova as well. The shock wave goes out many, many years, slows down over time. You get into different phases, once it hits different limits and things like that, and it starts slowing down basically once it's run into enough material. So it's really all just momentum, I guess is the answer.
Right, so then the population on the right is starting at a much higher velocity.
Yes.
So you're seeing it slow down.
Uh-huh.
Whereas the stuff on the left is already slow down.
Yeah, so what you're really seeing is just that is slowing down and becoming non-relativistic over time. As I said, well, once you no longer have this jet, then that really helps things slow down over time once you're no longer injecting that energy. And yeah, they're just eventually they become non-relativistic. So then, yeah, the question is, can you detect, if you found something, is it non-relativistic to begin with or not? The answer there is really just going to be if you found something that looked non-relativistic but very luminous, it was probably a former jetted one. So.
I'll ask a sociological question.
Yes, sir.
When you're dealing with energies of 10 to the 50 ergs,
Mm-hmm.
why do you use ergs?
Because astronomical convention is terrible. Did you see that I was using centimeters on those plots? Like, Jesus Christ, who thought that one up? I don't know. That's really honestly it. I need to talk to other astronomers and they use ergs, unfortunately. So. Yeah. So, but yes, I think some of the units here are just, yeah, like, does anybody know what 10 to the 16 centimeters is off the top of their head? I don't. I don't have a feel for that. So.
Oh, one more.
Yeah.
So is there a
The question was there a notable prize for the first discovery of a TDE? The answer is no, but the answer is also it's only 10 years. So these people are all still alive. So I guess we'll see. It's always next week, right? It's next week. Great to see you too. Oh, Miriam Israelowitz lives in Boston, and I hang out with her if you remember her, and she told me to say hi. Miriam Israelowitz.